again. Grothendieck vibrations, they were invented, discovered by Grothendieck in a series of steps. They are very useful mathematical objects, at least in my opinion. Certainly, Grothendieck used them throughout his work. They did not appear in the list of 12 useful mathematical ideas that Marco enlisted, but in that list, almost all those ideas required that notion. Before I start, I should give you another word of warning. Recently, I had the luck and opportunity to speak at seminars in presence, mostly with mathematicians. And in one case, I made a silly question. I asked a silly question. Of course, I can assume that everybody in the audience knows what a vibration is. And people went like this. So I spent a quarter of an hour on the blackboard. I'm not going to repeat that mistake. If you want, I ask the question. But so I'll give you a, well, I shouldn't say this, but I'll say it anyway, a very elementary presentation of what, for me, are Grothendieck vibrations. And the intuition that I have, and that it was brought forward from the beginning, is that a Grothendieck vibration, you will read just the word vibration on the slides throughout, because the fact that there is the adjective Grothendieck in front of the name vibration is because that word is very nice, and it's used for very different concepts in various areas of mathematics. So my vibrations are always Grothendieck vibrations. Vibrations are categories varying over a category. So it's almost obvious what they should be. A vibration is a functor, well, on the opposite category of the indexing category, which I will call most of the time base category, B for base, into the category of all categories. I will not worry about sizing because there are Grothendieck universes preventing me from making mistakes. So if you want, I'll be specific, but I'll drop that problem throughout. And well, I hope I've given you enough time to read the data for what a functor from the opposite of a category, and that appears in the last diagram down here, into the category of categories. It's, in fact, nowhere it's marked that the arrows are functors. Well, yes, here, just for the definition. So, examples. Oops, what happened? Oh, yes, before examples, I'm sorry. In mathematics, or at least in that part of mathematics where I move my little steps, a structure comes together with the notion of transformation from a structure to another, homomorphism. And once a notion is given by a category and a functor, it's almost obvious what a homomorphism should be. It's fairly complicated if you're not experienced with this notation, but it's a functor, it's a pair of things. It's a functor from the base to the other base, and according to the transformation between the bases, there are a natural transformation between the various categories that are given by the vibration. If you don't know what a natural transformation is, don't worry, they will not come in very often, but just to give you an idea that it is almost straightforward to define what a homomorphism of vibration is, at least with this approach. And so now, yes, and another thing, which comes out almost immediately by the picture, is that once I define a homomorphism to be something like this, it is possible to split, actually to get the homomorphism as composition of two specific homomorphisms, one where the first component is the identity, and the second where the second component is the identity. And I decided this morning, and that's why I wasn't remembering about this slide, that it would have been useful to just mention that this presentation of a homomorphism by means of a composite of two specific homomorphisms, let me mention what has become known as change of base on fibrations. It's just this kind of homomorphism. But just keep in mind that picture, and let's go to examples. I've given many examples, I hope, because I expect that you can connect at least with one or two of them, not necessarily to all of them. And here is my first list of examples. I try to be more specific. The first one, it's a very simple vibration from the point of view of structure. It takes sets as indexes, and to each set associates the poset given by the poset of subsets of the given set. So P of S is not just the power set, but is the power set with the inclusion relation for the order, and then the action on the arrows, on the functions. There are functions. Very few. Is not a function, actually. It's an arrow. It's an arrow in the opposite of the category of sets. And I've marked it red because I always get it wrong. The function is going in the opposite direction. The function is actually going from S prime to S. So marking it red is just to remind me that it's just a category theoretical notation for the arrows in the opposite category. But luckily, the function goes from S prime to S, and so the inverse image of subsets goes the other direction. From the power set of S, given a subset A of S, I can take its inverse image along the function S, F that goes from S prime to S to obtain F to the minus prime of A, which is a subset here. Okay, so, and it is a fibration with the definition I've listed there, because the category of posets is a full subcategory of the category of categories. More simply, every poset can be looked at as a category where the arrows are the pairs in the order relation. A slightly more complicated example, which is one of those which interest me in my specific research, and it's coming from the approach to logic promoted by Bill Lovier in the late 60s and the early 70s. Take a theory in first order logic and consider a formal category, which I call the category of context. They are usually called the category of context. Contexts are lists of three variables which are pairwise distinct. So I can use these variables to write formulas in the theory. An arrow, again, an arrow going from this list of y variables into the list of x variables is a list as long as that list. So there are as many terms here as there are variables here. And these terms are written in the theory using, at most, these variables. And that's why they're called contexts. I will connect to the talk that Brice Halimi had yesterday, which was very inspiring about context in languages. But this will happen when this picture will change slightly, although it will come from this. The word context that I'm using is technical. it's actually very technical. Here, I know precisely which letters I can use, and there is nothing I need to add to that. But forgive me, it's what it is, and I stick with it. No, but I hope I can relate to what you were saying. And well, I suggest also what could be done. But I must remember that I have to give you a functor. So on a list of variables, of distinct variables, I consider what's called the Lindenbaum-Tarski algebra of formulas within that, which use variables within this list. So not all formulas, but I'm slicing, I'm cutting the usual Lindenbaum-Tarski algebra that appears in algebraic logic to just formulas with at most the variables x1, xn. I'm marking here it's a pre-order because in the Lindenbaum-Tarski algebra there is an induced relation, which is a pre-order, which is reflexive and transitive, which says that a formula comes before another formula when, in the theory T, I can prove that the formula in the first position yields the formula in the second position. Phi yields Y, yields psi, gives me exactly the notion of pre-order. And mind you, it's not anti-symmetric just because when I prove an equivalence, I do not worry about the formulas being actually equal. The action on the arrows, again, the arrows here are marked in red because this is a list of terms in these variables y's, and they are as many as the variables x1, xn, because I want to use t1, tn to substitute into the xi's, and substitution of the ti's for the xi's gives me a functor from this pre-order to that pre-order. It's one of the standard properties of first order theories. So this is another example which links to logic. I made the mistake of adding it today because I saw this morning the presentation where actions of groups on another group by Homomorphisms was presented, and I thought that it might be useful. Think of a group as just a category with a single object where the element of the groups are the morphisms, the arrows, and consider the category which one object, a group H, and the arrows which are just the automorphisms of H, okay? And that is because this is a subcategory of the categories. It's an example of a vibration. What I thought was the simplest example I could propose. Fix any category C and consider, oops, this should not be post, this should be cat, and consider the functor that maps a set to the S power of the category C in the category of categories, and functions, a function again goes from S prime to S, act functorially on these categories by recomposition. Take any pre-shift. As a pre-shift, it maps into the category of sets, but a set is the same as a discrete category. I can embed fully the category of sets into the category of categories, and consider the pre-sheaf instead of mapping into set, mapping into cat. There is, well, that's just a picture of the pre-sheaf repeated with the wrong codomain, if you like. But as I say, I'm considering it with post-compose with that inclusion. And another example, which I hope you can see, another example, and probably the paradigmatic example of a fibration, given a category B with pullbacks, the fibration, which, now I move this back to this side, because I want, well, okay, I'll move it up there, okay? The fibration that maps an object to the comma category over the object, and an arrow in the category B, which is an arrow from B prime to B, with pulling back along F. And here's though I hit a wall, because it's one of those first exercises in an elementary course in category theory where you try to prove that when you go pull back and then pull back along another arrow and you compose the two, you get the same thing as you go pull back along the composition. And you test it in the category of sets, and it looks like it works because you're using only subsets, because that's an easy way to perform an example. And then you realize that actually there is something tricky with the way standard pullbacks in sets are constructed. And then you say, well, it's obvious there is another definition for a good choice of the pullback so that I can get it. And then you decide, well, I'm stuck. I stop this exercise. There must be a solution, but it's too difficult. And in fact, the solution always requires a use of the axiom of choice. It doesn't work. And this doesn't work because now yes, there we go. And so the definition is not quite right. I want something that is almost a functor, and it's so almost a functor that is called a pseudo-functor. What is a pseudo-functor? Here it is. It's a slight variation from the definition of functor. In fact, this is essentially cut and paste from the other slide. It's just that the slide doesn't stop here. Identities have disappeared, and they are just equal up to isomorphism. They're not canonical isomorphisms in the sense that was used yesterday. There are isomorphisms for all possible diagrams, and these isomorphisms must satisfy certain conditions to make sense, and they do make sense. But this is a requirement, and it's a, well, I don't know. It's a diagram of natural transformations. And here I'm comparing this natural transformation, which is easy to read because this composite is P of F, and it goes from P of F to P of F, so it's just the identity. But here, there is a composition of natural transformations, and if you're not used to using natural transformation, you see that this natural transformation cannot compose with that natural transformation, and you're right. Because what I mean in this diagram is that the composition I'm looking at is this natural transformation composed, prolonged with this functor to produce a natural transformation between this composite functor and this composite functor. And that natural transformation now goes from this composite, it goes into this composite, so I can compose it with this other to get a natural transformation which goes from the same domain to the same codomain as the other. And the request is that these two are equal, but that's not all. There is also this one. But now that you've learned how to look at natural transformations, you know what I should mean with that diagram. And there is another one. And here, these two natural transformations connect almost rightly. But here, you have to look carefully at the diagram and understand that, yes, they do compose, and they should be right. Oh, mind you, it's just saying that essentially the isomorphisms that you are using are behaving correctly to make things, to keep things straight, but it's just an intuition. And why just these diagrams? And then comes the beautiful solution. This is really where I think beauty comes in. Grothendieck comes up with a completely different point of view. Oh, he was the one who introduced vibration and pseudo-functors. He is the one who introduces also this notion. And the vibration is no longer a functor, a pseudo-functor from the opposite of the base category into the category of categories. No, it's something completely different, and I'm quoting, into the base B from another category, from what is called usually the total category of the vibration. And it's a functor in this direction, but this functor has a universal property. And the universal property is the thing that I'm just about to show you. Given any object in the upper category, which is taken by the functor into the object B, so B is P of E, and given any arrow in the base category, there this is not a commutative diagram, mind you, because this arrow in this upper category and this arrow is in the lower category. There is an arrow in the upper category, which is mapped by the functor down to F, and this is universal with that property. So any other time I can find an arrow in the base which is P of an arrow above with an object that maps into E, this must come from a unique composite from the original arrow Fn. And this does it. The names, as we've heard already yesterday, and please correct me if I do not quote correctly, the name usually applied to this construction, this is the Cartesian lifting of F, the Cartesian lifting to E, and this is a universal property. And now, well, I've not listed the definition of homomorphisms because a homomorphism is, well, if you play a category theory game, you know what to do. It's a pair of functors from the appropriate category to the correct category on the other side, which makes the square that gets generated commute, and such that Cartesian lifting are preserved. It's just that now requiring Cartesian lifting being preserved, since they're just solutions to universal problems, you know that the preservation is only up to isomorphism. And this clears the problem. How am I doing with time?
Fine.
Yeah, because I could stop here. And that's my point. And I should say here, and I'm very pleased to say, I'm honored to say that as I confessed yesterday, I never met Grothendieck, but I met many times Jean Benabou. And essentially what I'm putting forward is his idea, which he kept promoting through his life, that the right way to look at vibrations was this one. And it's a very simple categorical notion. It's not very simple, but it's in line with elementary category theory. How to go between pseudo-functors and vibrations. I mean, after all, I presented you pseudo-functors, and I'm saying this is the same as the vibrations that I introduced now. Well, let's go this direction from vibrations to pseudo-functors. And I'm going to, in fact, take advantage of what Brice did yesterday, because I'm repeating what he said. Given a vibration, the pseudo-functor is generated taking the over each object in the base the category of vertical arrows in E, the vertical arrows over the object B consist of objects which are mapped by the functor to B and arrows which are mapped by the functor into the identity on B. And re-indexing requires a choice, but once you've made the choice for the objects, everything else fits into place because it's a universal solution, as I said. The other way around, I find, well, certainly slightly more interesting. One has to glue together, I used the wrong word, has to add together, maybe it's better, all the pieces given by the pseudo-functor, all the categories PB, and they have to be added together by keeping them well-conned for each object B prime, B, whichever. Consider the pair of B and an object in P of B, and for an arrow that connects one such object with another, well, you have to use two arrows, one in P of B prime, and then connect B prime to B by F. The composite is, for a pseudo-functor, is given by this formula. And if you wonder why I wouldn't stop just there, which looks like a nice definition, is because pseudo-functors fail to be functors. In fact, I've tried to picture what a composition in a category is, and I wanted to do it because so one can see that essentially, you see, an arrow, the arrow from B prime alpha prime to B alpha is essentially going down in the category PB prime, but going down to the object that this is connected by F to the actual object where I wanted to end. Think of the actual arrow as going diagonally like that, and the composite must end here. While if I transform H via PG, oops, I get there, which is the wrong object, and I have to correct it by the isomorphism that was available to me. How does the picture changes from moving from pseudo-functors to vibrations in the last definition, which is the official definition? Well, I'll show you some of the examples that I had. I considered the functor, because this was a functor, which was the power set. Well, a picture in the form of one category and a functor into the base category, which is the category of sets, suggests that I consider this category of diagrams where the objects are inclusions of a subset into a given set, and arrows are just commutative diagrams. And it's, I don't know, it's a nice picture of a category. The important point, which I don't know I've ever tested in my courses, is that the functor that gets the codomains of the diagram, of the commutative diagram, is a vibration. And I'm not going to convince you of that because it is the vibration constructed via the Grothendieck construction from the pseudo-functor. And now the category, the pseudo-functor of Lindenbaum-Tarski algebras. The total category is essentially the original Lindenbaum-Tarski algebra on the theory, because, well, this is not the usual logical notation. One would probably write phi of x1 xn to mean a formula which is written using at most x1 xn. This is standard in logic. Well, I need to be more precise. I want to be more precise. I take a list of variables, and phi is paired with that list because phi is written using at most the variables that appear here. And this is psi written with at most these variables. But then, instead of looking at the usual pre-order on the global Lindenbaum-Tarski algebra, I look at the category which is given by, well, by this condition. So it's a list of terms which can be substituted for the x primes, and there is an error like that when I can prove that phi of x, if I may say it like that, entails psi of t of x, which is, well, as we were saying today at lunch, it's a fairly obvious way of picturing a category of definable sets, definable in the theory, the phi x1 xn, and arrows. Not really the usual category of definable sets, but very close to it. The example of a group acting on another, when I perform the Grothendieck construction on that pseudo-functor, I get the semi-direct product. Mind you, psi is acting on the left, and so that's the reason why the product is written like that. But it's just a resemblance of the general formula for composition that I showed you a few slides ago. I'm not going back because there are too many slides. Adding all the powers of C, one next to the other, gets me as a total category, the category FAM C, which is depicted here quickly. They are families of objects in C, and arrows are like this, a family of arrows with a certain indexing, and I've listed this because this is the universal solution to the problem of adding arbitrary co-products to a given category C, and it appears as a fibration. A pre-sheaf looked at as a pseudo-functor is just what is called the discrete fibration. I stop here for a second. Toposes, well, start with Grothendieck toposes, start with toposes of pre-sheaves, and then one moves to subcategories which are usually toposes of sheaves for a certain Grothendieck topology. They can be viewed, and they can be usefully viewed as fibrations. Discrete means that they do come from unstructured categories, discrete categories. And in a sense, fibrations, the category which I've not defined, but I'm sure you can guess, the category of fibration is very big. All the toposes of pre-sheaves sit within it. Sheaves, because they are contained in a topos of pre-sheaves by definition, they are subcategories of the category of fibrations. And finally, the non-working example of my first definition gives rise to the traditional cold fibration, where the category here B2 is 2, where 2 is the category with this non-trivial, single non-trivial error, is the category of diagrams, and the fibration takes the codomain of the diagram. It's an extension of the case of the of the pseudo-functor given by the power set and the corresponding vibration. Well, thank you. I want to add one final comment, and here I am going to turn slightly technical. The original definition of vibration, if I may say, the one which was wrong for certain examples, reappears as a particular case of the general vibration. And there is a characterization, but I really didn't want to go into it. And so I took advantage of all the things I've told you already. A vibration in the sense of the final correct definition is a functor of this form, which is a vibration, which comes from the Grothendieck construction applied to a functor, a real functor of this kind of index. By elementary algebraic category theory, the category of split vibrations, what is the category of split vibrations? Is the full subcategory of the category of vibrations on these objects. And I'm staying at the one level. I'm not talking about the two level, but there is also a higher level. The category of split vibration on a category B is just the category in the pre-sheaf topos over B. Well, one says then, how can you perform pre-sheaves over sets? As I told you, I can use Grothendieck universes, but do not worry about sizes. Examples of split vibrations, well, all the examples that I've constructed coming from a real functor. So essentially in this list, you don't see the codomain vibration because that was the only example that didn't work. Other examples, fix an object A in B, the domain functor from the comma category of arrows into A down to B. So given an object in this category, an arrow from B into A in the category B, call it E, this is sent by unit of A to the domain, to the object B, given, and now I have to show you how to lift an arrow F over B to E, and given an arrow F in B, it's one of those exercises that makes you so happy when you perform category theory because the solution is in front of you and it's there. It's more difficult to convince yourself that it does work because it seems so impossible, but it does. Or if you want, you've already studied the Yoneda theorem and the Yoneda lemma. Oh yes, I have time to tell you a little story because I was really happy to listen to Daniele this morning because he reminded me of when we were together, young students after our degree in mathematics, and we were in Italy attending. There was at that time no PhD program running, so after your unique degree in mathematics, you had to look for advanced courses, and I attended an advanced course, I think, in algebraic geometry, and the fantastic lecturer that was giving that course in algebraic geometry at a certain point hit me by saying, how could a mathematical theory be interesting if its first result is a lemma? He changed his mind. 20 years later, but he changed his mind. But also, you know very well how the Italian school of algebraic geometers is very strong and tough. And it's a hard life with them. Sorry, it was my mistake. It's not the Yoneda theorem. I don't know how I managed to. It's Yoneda lemma. Never mind. It's because I was thinking of the Yoneda fibration. I've learned how to play the game, and here consider I had to show you the category immediately. It's not the category of commutative diagrams. It's a category that connects arrows in B when they can fit in a diagram like that. So there is an arrow going in one direction and the other arrow is going backward. And of course, projecting down on the two domain and codomain and the arrows makes one of the arrows going in the wrong direction. That's why this is red, because it's in fact an arrow in the opposite category of where F1 lives. Okay, and that's also a fibration for the same reason why the first I presented is a fibration. That's already the Cartesian lifting. And then two more examples. One which at least from my experience is extremely useful, which allows to turn an internal category in a given category B. If you don't know what an internal category in a category, don't listen to me for the next 30 seconds, and make that look like a real category where not a real category, but a fibration with base B by homing from each object into the category object. And again, because Daniele Stoke suggested it to me when he mentioned how to change topologies on a set, the forgetful functor from the category of topological spaces to the category of sets, which is almost like one of the examples that Brice added. Is not exactly the same one, but also this one is a fibration. And if you want to think of the pseudo-functor going in the other direction, consider that over a set S, there is the partial order, because it is just a partial order, of all possible topologies over that set. And when you choose a topology, you are actually deciding which object to pick above a set in that fibration. And to give an overall picture of what I mentioned, there is, well, I let you imagine, and I hope you did imagine, a category of vibrations with a fixed base. There is the category of split vibration with a fixed base, and the construction I presented of going from a vibration to a pseudo-functor and from a pseudo-functor to a vibration can be turned into a pair of left adjoint in the sense of the fiber Yoneda lemma, where please note that although I know you would expect here an isomorphism, there is an equivalence of categories. The construction is the one I said. But if I modify that slightly and I take any functor into B, I get a right adjoint to the forgetful functor from split vibrations into this larger category of vibrations. And a right adjoint composed with a left adjoint give rise to a comonad on the category of categories into B, and the result that a master student I had in Genoa, Luca Mesiti, who is now in Leeds, happily performing his PhD, proved is that the pseudo coalgebras for that comonad, and if you don't know the words I'm saying, I'm sorry, but I will not go into the details. They are almost coalgebras. They are coalgebras up to appropriate isomorphisms, which are not canonical. They satisfy specific properties. And he proved that the pseudo-algebras are precisely the vibrations over B. And then we weren't quite certain that the result could be correct. So we checked with Thomas Stryker and Thomas, who wrote a very nice collection of notes on vibrations, which are available online, confirmed that yes, he was not aware of that result and that it looked correct. So I'm happily telling you about it. As a corollary of this, one finds that every vibration is an appropriate retract of a split vibration. And with this functor preserving Cartesian lifting and embedding homomorphically a vibration into a split vibration allows one to perform the split vibration completion of a vibration, turning a vibration into a split one, which is something rather complicated and unpleasant, as something very co-algebraic. And I think I've told you all I wanted to tell you.